An object from another star system passes through our solar neighborhood, and suddenly, the question isn't just what it is, but how we decide. Is 3I Atlas evidence of alien technology, or a familiar cosmic body behaving exactly as physics predicts? In this episode, astrophysicist David Kipping breaks down the 10 so-called anomalies behind the controversy and explains why extraordinary claims demand more than speculation. From interstellar objects and NASA's priorities to the James Webb Space Telescope, black holes, and the search for intelligent life. This conversation strips away hype and focuses on what the data actually says. If you value clear thinking in big cosmic questions, like the video, subscribe, and stay with us, because the universe is expanding, space itself is stretching. And that creates situations where objects can arrive from far beyond our solar system. Among those objects, one in particular has drawn intense attention: 3I Atlas. Some have argued that it could be an alien spacecraft passing through our neighborhood. Part of the reason it stands out is its speed. Objects like this are expected to pass through the solar system extremely rarely, perhaps once every several 100,000 or even 1,000,000 years. Yet within only 3 to 4 years of actively searching, astronomers have already identified 3 such visitors. That timing alone has raised eyebrows. The argument put forward by Avi Loeb is that if an object this large appears this frequently, then it may not be natural. That claim has landed in a broader context where public interest in space science is already high. NASA operates on an annual budget of roughly $25 billion, though only a fraction of that is used to build and operate space telescopes. Even so, discoveries like this can quickly move beyond professional circles. Some people have reacted with real concern, while others are simply fascinated. At the same time, discussions about black holes, multiverse, and the limits of physics have added to a sense that reality itself might be more flexible than it appears. Black holes, in particular, are sometimes described as places where space and time behave in ways that feel like shortcuts through the rules we are used to. Ideas about falling into one, watching time slow, or seeing the universe age around you are often mentioned, along with credible scientific reasons why a multiverse could exist. All of this forms the backdrop against which 3I Atlas entered public conversation. When people ask whether 3I Atlas poses any danger, the scientific answer is calm. There is no indication that it threatens Earth. While some individuals are alarmed, that reaction is not coming primarily from the scientific community. Researchers are interested, but measured. What has been unusual is how strongly the topic has spread through popular culture. Well-known public figures have commented on it, and social media has amplified speculation. This attention is a double-edged sword. It is encouraging to see people engaged with science, but it also leads to confusion, where careful analysis and dramatic interpretation are blended together. As a result, some people worry unnecessarily, while scientists emphasize that there is no reason for panic. There is a great deal to explain, and it begins with understanding what 3I Atlas actually is. The term 3I Atlas means third interstellar object. The word interstellar indicates that it originated outside our solar system. Astronomers have confirmed 3 such objects so far. The first was Oumuamua, discovered around the year 2017. Its name comes from Hawaiian and means messenger from afar. That object also attracted attention because its behavior and inferred shape were unusual. Artist impressions showed it as elongated, sometimes described as cigar-shaped, which caused public speculation. It is important to note that these images were not photographs. The object was too small and distant to resolve directly. Instead, astronomers measured how its brightness changed over time. As it rotated, the reflected light rose and fell in a regular pattern. From that pattern, scientists inferred its shape. The data suggested either a very thin, elongated form or a flattened, pancake-like shape. Both possibilities were strange, but neither required non-natural explanations. The second interstellar object, named 2I Borisov, behaved much more like a typical comet. It showed clear signs of gas and dust being released as it approached the Sun. The third object, 3I Atlas, appears to be similar. It is almost certainly comet-like as well. That means it contains ice mixed with dust and rock, rather than being a solid, inert body. To understand how such objects are found, it helps to know how astronomers search for asteroids and comets. Planets move slowly across the sky, so they appear in nearly the same place night after night. Small bodies are different. They move quickly and are faint. An object roughly 1 kilometer across, located several astronomical units away, reflects very little sunlight against the black background of space. It is difficult to detect. Astronomers take repeated images of the same region of sky and look for points of light that shift position. When a dot moves noticeably from one image to the next, it signals something nearby and fast-moving. By tracking that motion over time, scientists can calculate an orbit. If the orbit shows that the object is not bound to the Sun, but instead passes through once and leaves, it is classified as interstellar. 3 such objects have now been identified. The first appeared more rock-like, while the second and third clearly behaved like comets. Their existence was predicted long before they were found. During the formation of planetary systems, young stars are surrounded by disks of gas and debris. As planets form, especially giant planets similar to Jupiter, their strong gravity can fling smaller bodies outward. Some of that material gains enough speed to escape its home system entirely. Over billions of years, this process should populate the space between stars with countless wandering objects. Occasionally, one of them passes close enough to another star to be detected. Before these discoveries, estimates suggested that we might see one such object about once every 10 years. Finding 3 in just a few years was surprising. Improved telescopes have played a role, as modern surveys are far more sensitive and scan the sky more frequently. Even so, the number detected is higher than expected. Predicting these rates involves significant uncertainty. Scientists base their estimates largely on what is known about our own solar system. They count how many asteroids and comets exist in regions like the asteroid belt between Mars and Jupiter, and the Kuiper belt beyond Pluto. They then simulate how planets scatter material over time. From those simulations, they estimate how many objects should be ejected into interstellar space. The fact that observations do not perfectly match predictions is interesting, but not necessarily alarming. The solar system itself is not typical in many ways. Studies of exoplanets, planets around other stars, show that many systems look very different from ours. Some have giant planets extremely close to their stars. Others lack structures like our asteroid belt. Given that our system is unusual, it may not be a good template for estimating how much debris other systems produce. In that sense, the discrepancy does not automatically point to something artificial. Still, 3I Atlas has been highlighted because of a list of reported anomalies. Avi Loeb has presented 10 points that he argues are difficult to explain with standard comet models. Individually, Each point might not be decisive. Taken together, he suggests they could indicate an artificial origin. These claims have circulated widely through podcasts and blogs. At present, 3I Atlas is positioned roughly behind the Sun from our point of view, making detailed observations difficult. This limits what can be measured directly and increases uncertainty. Other researchers have responded by examining each claimed anomaly in detail. They have shown that many of the points can be explained through known physical processes, such as how cometary ice releases gas, how dust affects brightness, and how observational limits shape what we think we see. This kind of back and forth is normal in science. Competing interpretations are tested against data, and explanations that rely on the fewest additional assumptions tend to prove more durable over time. In the case of 3I Atlas, this process begins by separating the individual claims and examining them one by one. The first of these focuses not on what the object is made of, but on how it moves through space. The first anomaly centers on the object's trajectory. 3I Atlas is moving on a retrograde path, meaning it travels in the opposite direction of most planets. And that path is aligned within about 5 degrees of the ecliptic plane. The ecliptic plane is the flat disk in which the planets orbit the Sun. If the solar system were visualized as a thin pizza, nearly all the planets would move along the surface of that pizza rather than cutting sharply up or down through it. The claim is that a random object arriving from interstellar space should not, by chance, line up so closely with that plane. The probability of such an alignment is sometimes estimated at roughly 2%. At first glance, that does sound unusual. Stars across the galaxy are oriented randomly, so debris ejected from other systems should arrive from all directions with no strong preference. However, there is an important observational factor to consider. The surveys used to discover asteroids and comets do not scan the sky evenly. The survey that found this object is called ATLAS, which is also where the name 3I Atlas comes from. These telescopes spend far more time observing near the ecliptic plane, because that is where most known comets and asteroids in our own solar system are found. Much less attention is given to regions far above or below that plane. As a result, objects traveling near the ecliptic are simply more likely to be detected. This creates what scientists call a selection bias. In practical terms, it means we are more likely to notice things where we are already looking most carefully. From that perspective, the alignment is not surprising. There is also the question of how unusual a 2% probability really is. In scientific work, low probabilities occur frequently. Many natural processes produce outcomes that seem unlikely in isolation but are expected when large numbers of events are considered. A 2% chance does not require an extraordinary explanation by itself. A natural object can arrive at that angle without violating any known physics. This is why the alignment alone is not considered strong evidence of an artificial origin. It is one point among many, which is why additional anomalies are often discussed. The second anomaly involves the object's appearance during observations made in July and August of the year 2025. During that time, 3I Atlas showed what is described as a sunward jet or anti-tail, unlike the familiar tails of comets, which point away from the Sun. This structure appeared to point roughly toward it. The claim is that this is not a visual illusion caused by geometry, but a genuine physical feature. To understand this, it helps to review how comet tails form. A comet is essentially a mixture of ice, dust, and rock, sometimes described as a dirty snowball. As it approaches the Sun, heat causes the ice to turn directly into gas, a process known as sublimation. This releases water vapor, carbon dioxide, carbon monoxide, and other gases. These gases form a surrounding cloud called a coma, which is like a temporary atmosphere around the comet. The Sun continuously emits a stream of charged particles known as the solar wind. This wind pushes the gas and dust away from the Sun, creating the familiar tail that stretches behind the comet, often for millions of kilometers. In the case of 3I Atlas, early images showed material concentrated on the side facing the Sun, creating the appearance of an anti-tail. While this seems strange, it is not without precedent. Other comets have displayed similar features in the past. At least two well-documented cases exist, including a comet observed in the year 2014 and another seen in the 1970s. In those cases, the anti-tail was explained by the physical conditions of the comet and its distance from the Sun. Distance matters because the strength of the solar wind decreases with increasing distance. During the period when this object was first imaged, it was located beyond the orbit of Mars. That is farther out than where comets are usually observed in detail. Normally, astronomers focus on comets when they are closer to Earth and closer to the Sun, where their activity is more dramatic. 3I Atlas was observed intensively at a greater distance because of the unusual interest surrounding it. At that distance, the solar wind is much weaker. Using a simple analogy, it is like turning a hairdryer from a strong setting down to a very gentle breeze. Gas still escapes from the sun-facing side of the comet, because that side is being heated, but there is less force to blow that material backward into a long tail. The result is a buildup of material on the side facing the Sun, which can appear as an anti-tail. As the object moves closer and solar activity increases, a more conventional tail becomes visible as well. In fact, 3I Atlas shows both a coma and a tail, which are the defining features of a comet. The solid core, called the nucleus, remains hidden deep inside this cloud of gas and dust. It cannot be directly seen because the surrounding material is so extensive. This object has been observed by major instruments, including the Hubble Space Telescope and the James Webb Space Telescope, as well as by skilled amateur astronomers using large backyard telescopes. The images show a diffuse, cloudy structure rather than a solid surface. That appearance is exactly what is expected from an active comet. Spectroscopy has also been used to study the light coming from the object. When that light is spread into its component colors, specific absorption patterns appear. These patterns reveal the presence of water, carbon dioxide, and other common cometary gases. This technique, known as spectroscopy, is a standard method for determining chemical composition at a distance. Taken together, these observations point strongly toward a natural explanation. The gases being released, the structure of the coma, and the development of a tail all match what is seen in ordinary comets. From this perspective, the appearance of an anti-tail does not require an exotic cause. It follows logically from the object's composition, its changing geometry relative to Earth, and the physics of solar heating and solar wind. As a result, this second anomaly is generally viewed as observationally interesting, but not decisive evidence of an artificial origin. With the object's visible behavior largely accounted for, the discussion moves away from what can be directly seen and measured, and toward what must be inferred indirectly. The third anomaly focuses on the estimated mass of 3I Atlas. The claim is that its nucleus is about 1 million times more massive than Oumuamua and roughly 1,000 times more massive than 2I Borisov, while also moving faster than both. When these factors are combined, The likelihood of such an object appearing is sometimes described as less than 0.1%. This argument, however, depends almost entirely on how the mass is calculated, and that is where the uncertainty begins. Measuring the mass of a comet is extremely difficult. In astronomy, mass is usually determined through gravity. If an object has something orbiting it, the mass can be inferred from the orbit. For example, the mass of Mars can be calculated by studying the motion of its two moons, Phobos and Deimos. By measuring how far away those moons are and how long they take to complete an orbit, and then applying Newton's version of Kepler's laws, the mass of Mars can be derived with high precision. This method works well when there is a clear gravitational interaction to observe. A comet does not offer that advantage. It has no moons, and its gravity is far too weak to noticeably affect planets, the Sun, or even nearby asteroids. It does not tug on anything in a way that can be measured. That removes the most reliable method astronomers have for weighing objects. As a result, indirect approaches must be used instead. One such approach is to estimate how much material the comet is losing. As gas and dust stream away from the nucleus, astronomers can measure the brightness of that material and analyze its spectrum. From this, they can estimate the rate at which mass is being lost. The idea is then to work backward and infer how large and massive the original nucleus must be to sustain that level of activity. In principle, this sounds reasonable. In practice, it is extremely challenging. It requires detailed modeling of how different ices sublimate, how heat flows through the surface, how various molecules interact, and how dust is carried along with gas. Small changes in assumptions can lead to very different results. The calculation presented in support of the anomaly is closer to a rough, back-of-the-envelope estimate than a full planetary science analysis. It provides an order of magnitude guess rather than a precise measurement. That does not mean it is useless, but it does mean it should be treated with caution. Planetary scientists, who specialize in comets and small bodies, have been particularly skeptical. Their view is that this is not how mass estimates are normally done in their field, and that the uncertainties are too large to justify a strong conclusion. Some argue that the true mass could be far lower than claimed. This disagreement matters because the argument hinges on size. In natural systems, there are far more small objects than large ones. This pattern appears everywhere, from broken rocks to cosmic debris. When objects collide and fragment, they tend to produce many small pieces and only a few large ones. In planetary systems, this means there should be countless small interstellar objects and very few large ones, even after adjusting predictions to account for the fact that more interstellar objects have been detected than expected. The largest ones should still be extremely rare. The claim is that if 3I Atlas really is as massive as suggested, then it is simply too big to appear so soon. An object of that size should pass through the solar system perhaps once every several 100,000 or even 1,000,000 years. Detecting it within just 3 or 4 years of starting systematic searches would be extraordinarily unlikely. From that perspective, the conclusion is drawn that it cannot be natural. However, this conclusion rests on the mass estimate being correct. If that estimate is off by even a modest factor, the statistical argument weakens dramatically. Small errors in assumed size or density can translate into large differences in expected frequency. This is why many researchers hesitate to treat this point as settled at present. There is no direct measurement that confirms the object is as massive as claimed. Speed is often folded into this discussion as well. 3I Atlas entered the solar system at a velocity of roughly 60 kilometers per second. Typical objects bound to the solar system move at speeds closer to 20 to 30 kilometers per second. This makes 3I Atlas 2 to 3 times faster than most familiar bodies. That speed is unusual. But it also carries information. Over long periods of time, interstellar objects can gain speed through repeated gravitational encounters. As stars move through the galaxy, they occasionally pass close enough to exchange energy with passing debris. Each encounter can act like a small gravitational assist. Similar to the way spacecraft gain speed by swinging past planets, the older an object is, the more opportunities it has had to experience these encounters. For that reason, higher speeds tend to suggest greater age. This reasoning is statistical rather than precise. It cannot tell us that an object is exactly 8 billion years old, for example, but it does suggest that 3I Atlas is likely very old, possibly older than the solar system itself, which formed about 4.5 billion years ago. The Milky Way galaxy is estimated to be around 13 billion years old, and the universe as a whole is about 13.8 billion years old. An object moving this fast could plausibly be more than half the age of the universe. Determining the age of a galaxy is not straightforward. A galaxy is not a single object with a clear birth date. It grows and changes over time, merging with other galaxies and forming new stars while older ones die. Astronomers estimate the age of a galaxy by studying the ages of its stars, since a galaxy is essentially a collection of stars. This provides a useful proxy. Our galaxy, the Milky Way, is considered mature, with its earliest components forming not long after the universe itself began. Galaxies are also not static. The Milky Way is surrounded by smaller satellite galaxies, such as the Magellanic Clouds, which it is gradually absorbing. It is also on a collision course with the Andromeda Galaxy, the nearest large galaxy to our own. In roughly 5 billion years, the two will pass through each other and eventually merge. Despite the dramatic language, individual stars are unlikely to collide. The distances between stars are vast, even during a galactic merger. What will happen instead is a slow gravitational dance, with the two galaxies oscillating through one another until they settle into a single, larger system, sometimes informally called Milkdromeda. Events like that underscore how dynamic the universe is on long timescales. They also highlight how limited our perspective is. When we talk about the age of the universe, we are constrained by the speed of light. Because light travels at a finite speed, we can only see a limited region of space, even though the universe is about 13.8 billion years old. The expansion of space means we can observe objects that are now about 45 billion light-years away. Beyond that, light has not had time to reach us. This boundary sets a hard limit on observation. No matter how powerful a telescope becomes, it cannot see beyond the earliest light emitted by the first stars and galaxies. That limit is defined by physics itself, not technology. The James Webb Space Telescope was built to approach that boundary as closely as possible. Its goal is to observe the faint infrared light from the earliest cosmic structures, giving insight into how the first stars and galaxies formed. The telescope represents an extraordinary technical achievement. It was designed to unfold in space through a complex sequence involving more than 200 moving parts. Unlike the Hubble Space Telescope, which orbits Earth and can be serviced by astronauts, the James Webb Space Telescope operates far beyond the Moon. At a distance roughly 4 times greater, no human has ever traveled that far, and there is no plan to service the telescope in person. It was designed as a set-it-and-forget-it mission. If a critical component had failed during deployment, there would have been no way to fix it. The financial risk was just as large. The total cost of the telescope approached $10 billion. NASA's annual budget is about $25 billion. And only a small fraction of that is allocated to building telescopes. Committing to a single mission of this scale required decades of sustained focus and meant that many other projects were delayed or canceled. For years, much of the available funding was tied up in making sure this one telescope succeeded. Astronomers understood the potential rewards, but they also recognized the danger of concentrating so many resources into a single effort. It was, in many ways, a decision to place nearly everything into one basket, trusting that the scientific return would justify the gamble. If that basket were to fail, the consequences would extend far beyond a single mission. This possibility forced the astronomical community to think carefully about alternative paths. Researchers began asking what other kinds of observatories might have been built with the same investment, and whether spreading risk across multiple instruments could offer a different balance between ambition and reliability. As a result, when the community was invited to propose major future observatories, several distinct concepts emerged. These included designs centered on smaller telescopes, distributed networks of instruments, and observatories operating at wavelengths very different from those used by Hubble or James Webb. One proposal was the Habitable Worlds Observatory. The goal of that telescope would be to take direct images of planets similar to Earth orbiting other stars. James Webb can image planets, but only under specific conditions. It is best suited to very large planets or planets that are still forming. Young planets are extremely hot, almost like molten worlds, and they glow brightly in infrared light. That makes them detectable. A mature Earth-like planet orbiting a Sun-like star is much cooler and far dimmer. James Webb cannot separate that faint signal from the overwhelming glare of the star. A telescope designed specifically for that task would need advanced optics and light-blocking systems far beyond what Webb was built to do. Another major proposal focused on X-ray astronomy. X-rays are a completely different part of the electromagnetic spectrum. Humans see visible light in a narrow range, roughly from 400 to about 700 or 800 nanometers in wavelength. Infrared light, which James Webb observes, has longer wavelengths and lower energy. There is a direct relationship between wavelength and energy. The longer the wavelength, the less energy each photon carries. Infrared light comes from relatively low-energy environments, such as warm planets or the surfaces of stars. Shorter wavelengths carry more energy. Ultraviolet light is more energetic than visible light, which is why it can cause sunburn. X-rays are far more energetic still. They pass easily through soft tissue and can only be produced in extremely violent environments. When matter falls into a black hole, when neutron stars collide, or when massive black holes merge at the centers of galaxies, X-rays are released. These events represent the most extreme conditions in the universe. An X-ray supertelescope would allow astronomers to study black hole mergers, active galactic nuclei, and quasars in unprecedented detail. It would open a window onto the high-energy universe, revealing processes that cannot be seen at lower energies. Each type of telescope answers different questions. An X-ray observatory would tell us nothing about life or habitable planets, but it would dramatically improve our understanding of how the universe behaves under extreme conditions. James Webb, by contrast, was never primarily designed to study planets or life. Its core mission was to observe the first stars and galaxies that formed after the universe began. That goal explains why it was built as an infrared telescope. When a galaxy forms, it emits light mostly in the visible range. But if that galaxy is billions of light years away, the expansion of the universe stretches the light as it travels. What began as blue or visible light becomes red, then infrared. By the time it reaches us, to see the earliest galaxies, a telescope must be sensitive to infrared wavelengths. That requirement dictated the entire design of James Webb. Discussions about extreme physics often circle back to black holes. When people hear about black holes colliding, the question naturally arises, what does that actually mean? Stars evolve over time. The sun is not massive enough to collapse into a black hole. Left alone, it will not become one. Only stars far more massive than the sun end their lives that way. Many of these massive stars exist in pairs, known as binary systems, or even in more complex groupings. As these stars age, interactions between them can cause their orbits to shrink. Over long periods, they spiral toward each other and eventually merge. When two black holes merge, they do not collide like solid objects. Instead, they distort space itself. The merger sends ripples through space-time, known as gravitational waves. These waves are not light. They are changes in the geometry of space, propagating outward at the speed of light. Instruments such as the Laser Interferometer Gravitational Wave Observatory, known as LIGO, are designed to detect these ripples. So far, scientists have detected hundreds of black hole mergers this way. In a sense, these detectors allow us to listen to the universe rather than see it. A gravitational wave is similar in concept to a sound wave. Sound compresses and stretches air. Gravitational waves compress and stretch space itself. Under certain conditions, if a person were close enough to a merging black hole, those vibrations could, in principle, be converted into sound. Even in the vacuum of space, space-time itself can carry these waves. It is a radically different way of observing the cosmos. Distinct from the use of light that has dominated astronomy for centuries, future generations of gravitational wave detectors could be far more sensitive. In principle, they could detect every black hole merger within the observable universe. Anything that occurs within the region from which light has had time to reach us could also be detected through gravitational waves. Since those waves travel at the same speed as light, events beyond that boundary, known as the particle horizon, would remain forever inaccessible. But within that limit, it may one day be possible to monitor every major merger event. Questions about black holes inevitably lead to questions about time. Time does not behave the same way everywhere. A clock on Earth measures time differently than a clock placed near a black hole. As a clock approaches the event horizon, the boundary beyond which nothing can escape, its ticking slows relative to a distant observer. From far away, the clock appears to tick more and more slowly, until it seems to stop entirely at the horizon. This effect is known as gravitational time dilation. Imagine watching a person fall backward toward a black hole from a safe distance. As that person approaches the event horizon, they would appear to slow down. Light coming from them would stretch to longer wavelengths, shifting from blue toward red. This gravitational redshift happens because the light must climb out of an intense gravitational well, losing energy as it does so. The person would grow fainter and redder, eventually becoming invisible, frozen in time at the edge of the horizon from the observer's perspective. From a distance, a clock carried toward a black hole really does appear to slow down. Time itself behaves differently depending on where you place your observer. The closer that clock gets to the event horizon, the more extreme the effect becomes. To someone watching safely far away, the clock seems to tick more and more slowly, until it almost freezes in place. This is not a metaphor, it is a direct prediction of general relativity, confirmed in less extreme forms by experiments closer to home. What makes this unsettling is that the experience depends entirely on perspective. From the outside, nothing ever quite crosses the event horizon. The falling object appears to slow, fade, and become redder as the light climbing out of the gravitational well loses energy. Eventually, it slips beyond what our eyes and instruments can detect, seemingly suspended at the edge of the black hole forever. From the point of view of the falling object, however, nothing special happens at that boundary. It continues inward, passing a line that can never be reported back across. This is where black holes stop being just another astrophysical object and begin to expose a deeper problem in our understanding of reality. They create conditions where time, space, and cause and effect no longer behave in ways familiar from everyday experience. Beyond the event horizon, the physical descriptions we rely on begin to break down. The rules that work so well elsewhere no longer fit together, leaving a region that remains fundamentally inaccessible. That breakdown is not accidental. It reflects a deeper divide at the heart of modern physics. Black holes are places where space and time are pushed to their limits, and where two powerful theories are forced to operate side by side. Quantum physics governs the behavior of the very small, describing particles, uncertainty, and probability. General relativity governs the very large, explaining gravity, space-time, and cosmic structure. Black holes are the only known objects where both frameworks are required simultaneously in a direct and unavoidable way. This overlap is what makes them uniquely valuable to science. It is also what makes them so difficult to understand. At the edge of a black hole, the known rules still apply. But beyond that boundary, physics itself becomes incomplete. This difficulty shows up clearly in what is known as the black hole information paradox. At its core, the paradox asks what happens to information when something falls into a black hole. In quantum physics, information cannot be destroyed. Every process is reversible in principle. If an egg falls and shatters into countless pieces, quantum theory says that, at least in theory, it should be possible to reverse every motion and put the egg back together exactly as it was. Nothing is truly erased. A black hole seems to violate that rule. When an object crosses the event horizon, it cannot come back out. From the outside, all details about that object appear to be lost forever. If it were a book filled with text, all of those words, all of that structure and information would seem to disappear from the universe. Quantum theory does not allow that. According to its rules, information must always be preserved in some form. This conflict is why it is called a paradox. The two theories that work extremely well in their own domains give incompatible answers when applied to black holes. To resolve this, physicists suspect that the information must somehow escape or be preserved, even if we do not yet understand how. One idea that plays a central role in this discussion comes from Stephen Hawking. Using quantum reasoning, he showed that black holes should not be completely black. Instead, they should emit a faint form of radiation, now known as Hawking radiation. This radiation implies that black holes slowly lose mass over time and eventually evaporate. A simple way to picture this involves particle pairs that constantly appear and disappear in empty space. According to quantum physics, pairs of particles and antiparticles briefly pop into existence and then annihilate each other almost instantly. This happens everywhere, all the time. Near the event horizon of a black hole, One of these pairs can form right at the boundary. One particle may fall into the black hole, while the other escapes. When that happens, energy is carried away. To balance this, the black hole loses a tiny amount of mass over extremely long timescales. This process causes the black hole to shrink. This idea raises strange possibilities when combined with the effects of time distortion near a black hole. From certain perspectives, it becomes possible to imagine observing the black hole itself change or even evaporate while falling toward it, depending on how time is experienced along different paths. These are not practical scenarios, but they show how deeply our usual intuitions break down in these environments. This discussion sometimes invites comparisons to other quantum thought experiments. One famous example is Schrödinger's cat, which explores what it means for something to exist in multiple possible states at once. In that experiment, a system is set up so that a random quantum event determines whether a cat lives or dies, until the box is opened and observed. Quantum mechanics describes the system as a superposition, meaning both outcomes exist simultaneously. The deeper question is how observation fits into reality. In quantum mechanics, a system does not settle into a single outcome until it is observed. This leads to interpretations in which all possible outcomes actually occur, each in its own branch of reality. This idea is often called the many worlds interpretation, originally proposed by physicist Hugh Everett. In this view, the universe constantly branches, creating parallel outcomes for every quantum event. Under this interpretation, every possible version of an event exists somewhere. If a coin could land heads or tails, both outcomes occur, but in separate, non-communicating branches of reality. Over time, these branches multiply rapidly. Even small differences, such as choosing one word instead of another in a sentence, would lead to distinct versions of events unfolding side by side. Some thinkers have taken this idea to extreme conclusions, leading to a controversial concept sometimes called quantum immortality. The idea is not a recommendation or a practical experiment, but a logical extension of the many worlds view. In situations where survival is extremely unlikely but not impossible, there would always be at least one branch in which the individual survives, since conscious experience only continues in branches where the observer remains alive. It raises unsettling questions about what death means in such a framework. Pushed far enough, this leads to uncomfortable implications. If survival is always possible in at least one branch, then consciousness might never experience its own end. Instead, it would continue along increasingly improbable paths. Critics argue that this highlights a problem with the interpretation itself. The idea seems to conflict with how life is actually experienced and observed. Supporters respond that discomfort alone is not a reason to reject a theory if the mathematics supports it. The many worlds interpretation remains one of the most widely discussed views of quantum mechanics. Even though it challenges everyday intuition, it was proposed decades ago and continues to be debated. Its appeal lies in the fact that it removes the need for a special role for observation. Treating the universe as a single, continuously evolving quantum system, these ideas also intersect with questions about meaning and limits. If existence branches endlessly, or if consciousness could persist in unlikely ways, it forces a re-evaluation of how time, life, and purpose are understood. A finite lifespan gives structure and urgency to experience. The knowledge that time is limited shapes decisions, goals, and values. Removing that limit changes the entire framework. In this way, discussions about black holes, quantum mechanics, and multiple possible realities circle back to human perspective. Black holes are not just extreme objects in space. They expose cracks between our best theories and reveal how much remains unresolved. They sit at a point where physics stops giving clear answers and starts raising deeper questions. Not only about the universe, but about how reality itself is put together. Black holes often feel like breaks in the rules of the universe itself. They are places where space and time are pushed beyond their usual limits, and where some of the deepest questions in physics are forced to collide. One of the long-standing goals of physics is to bring together quantum physics, which governs the very small, and general relativity, which governs the very large. These two theories both work extremely well, but they do not naturally fit together. Black holes are the one class of objects we know where both sets of rules must apply at the same time in a meaningful way. That is why they sit at the center of so many unresolved problems. One of the most famous of those problems is known as the black hole information paradox. At its core, it asks a simple question: what happens to information when something falls into a black hole? In quantum physics, information cannot be destroyed. Every physical process is reversible in principle. If an egg falls onto the floor and shatters, quantum theory says that, at least theoretically, it should be possible to reverse every motion of every particle and reconstruct the egg exactly as it was before. Nothing is ever truly erased. Black holes appear to violate that rule. Once something crosses the event horizon, it cannot come back out. From the outside, all the details of that object seem to be lost forever. If it were a book, every word in it would be gone from the universe. Quantum physics cannot accept that outcome. According to its rules, information must always be preserved. This contradiction is why physicists call it a paradox. It signals that our current theories are incomplete when applied to black holes. One possible way out of this problem comes from the idea of Hawking radiation. Stephen Hawking showed, using quantum arguments, that black holes should slowly emit radiation and lose mass over time. They are not eternal. A simple way to picture this is to imagine pairs of particles constantly appearing and disappearing in empty space. Quantum physics predicts that these particle pairs form everywhere, even in what looks like a perfect vacuum. Near the event horizon of a black hole, one particle in a pair can fall in while the other escapes. When that happens, energy is carried away, and the black hole loses a tiny amount of mass over extremely long timescales. This causes the black hole to evaporate. This idea opens the door to strange possibilities. If time behaves very differently near a black hole, it becomes possible, at least in thought experiments, to imagine scenarios where the black hole itself changes or even disappears while being approached. These are not practical situations, but they highlight how far our intuitions fail in these environments. Discussions like this often drift toward broader questions about quantum mechanics itself. One famous example is Schrödinger's cat, a thought experiment designed to illustrate how quantum systems can exist in multiple possible states at once. In that scenario, a random quantum event determines whether a cat lives or dies, until the system is observed. Quantum mechanics treats both outcomes as simultaneously real. One interpretation of this behavior is called the many worlds interpretation. It suggests that every possible outcome of a quantum event actually occurs, each in its own separate branch of reality. This idea was proposed by physicist Hugh Everett in the middle of the 20th century. In this view, the universe is constantly branching. Every decision, every random event, produces parallel versions of reality that no longer interact with one another. Over time, these branches multiply rapidly. Even tiny differences lead to completely separate histories. Under this interpretation, there could be countless versions of the same moment unfolding side by side, each differing in small ways. This idea is unsettling, but it has remained influential because it removes the need for a special role for observation in quantum mechanics. Some people have taken this idea to extreme conclusions, leading to a concept sometimes called quantum immortality. The logic goes as follows. In any dangerous situation, there is usually a very small chance of survival. If all outcomes occur, then there will always be at least one branch in which the individual survives. Conscious experience, by definition, can only continue in branches where the observer remains alive. This leads to disturbing implications about whether death is ever experienced at all. Many physicists view this as a sign that something about the interpretation is deeply problematic. Others argue that discomfort alone does not invalidate a theory. These ideas naturally raise questions about time, mortality, and meaning. A finite lifespan gives urgency and structure to human experience. Knowing that time is limited shapes priorities and choices. Removing that limit changes the entire framework through which life is understood. From there, it is natural to wonder how perspective might change if human lifespans were extended, not to immortality, but to something much longer than they are now. If people lived for several hundred years, their relationship to long-term problems might shift. Issues like environmental change, resource use, and planetary health would no longer feel distant. They would fall well within a single lifetime. A longer horizon could encourage more patience and long-term planning, reducing the focus on immediate gain. At the same time, human societies are shaped by competition and tribal thinking. That tendency can be harmful, especially when it leads to conflict and division. But it also drives progress. Competition pushes people to improve, to innovate, and to reach beyond what already exists. This creates a tension. The same traits that enable technological advancement can also threaten long-term survival. That tension raises an interesting question about other civilizations. If intelligent life exists elsewhere, how might it balance cooperation and competition? A species with no competitive drive might never develop advanced technology. A species that is too competitive might destroy itself before it can spread beyond its home world. It is possible that this balance is rare, and that it limits how long technological civilizations can last. Against that backdrop, the discussion returns to 3I Atlas and the list of claimed anomalies. The fourth anomaly concerns the object's path through the solar system. It is said to be fine-tuned to pass within tens of millions of kilometers of Mars, Venus, and Jupiter, and to be observable from Earth near its closest approach to the Sun. The quoted likelihood for this configuration is about 0.005%. This claim is based on a statistical argument, and that makes it relatively straightforward to evaluate. The object does indeed pass near those 3 planets, but the solar system contains more than 3 planets. If a different set were chosen, such as Mercury, Earth, and Saturn, the probabilities would change immediately. When probabilities are calculated after the fact by selecting specific conditions, they can be made to look arbitrarily small. This practice is known as p-hacking. A p-value measures how surprising an outcome appears under certain assumptions. But if those assumptions are chosen selectively, the number loses meaning. By combining enough ordinary traits, almost anything can be made to seem extremely unlikely. This is why most scientific journals discourage or outright ban p-hacking. It has been especially problematic in fields like nutrition and health, where carefully chosen statistics have been used to support dramatic but unreliable claims. In this case, the low probability comes from selecting a specific set of planets after the trajectory is already known. If the object had passed near different planets, a different calculation could have been made. Passing near a planet is not unnatural behavior for a comet or asteroid. If the object had suddenly stopped, reversed direction, or executed a controlled maneuver, that would be a different matter. Nothing like that has been observed. Its motion follows the same gravitational rules as other small bodies. The fifth anomaly involves the composition of the gas released by the object. Spectroscopic measurements show water, carbon dioxide, and carbon monoxide, all of which are normal for comets. However, the ratio of nickel to iron in the gas plume appears unusually high. This is not something commonly seen in comets from our solar system. That observation is genuinely interesting. But context matters. 3I Atlas was observed much earlier in its journey toward the Sun than most comets. It has been monitored from a distance of about 3 astronomical units down to about 2 astronomical units. An astronomical unit is the distance between Earth and the Sun. During that time, the nickel to iron ratio has been changing. It started out extreme and has been moving closer to values seen in ordinary comets as the object approaches the Sun. The expectation is that, closer in, it may become indistinguishable from typical comet behavior. This suggests that the anomaly may be a result of observing the object at an unusual stage. Rather than evidence of something artificial, there may be many comets with similar properties that simply have not been observed under the same conditions. In addition, this is only the third interstellar object ever detected. There are only 2 others to compare it to. Drawing strong conclusions from such a small sample is risky. It is also worth remembering that 3I Atlas did not originate in our solar system. It came from another star system within the same galaxy. There is no strong reason to expect material formed around a different star to look exactly like material formed around our Sun. We already know that planets around other stars can be very different from those in our own system. It would not be surprising if comets from other systems also show unfamiliar properties. Objects like 3I Atlas come from other star systems within the same galaxy. They do not simply drift at random without cause. There are well-understood physical processes that can eject material from a planetary system and send it traveling between the stars. Our own solar system likely went through such a phase early in its history. Models of the young solar system suggest that it may once have contained an additional giant planet, similar in size to Uranus or Neptune. When astronomers simulate the early motions of the giant planets and speed up the calculations, close gravitational interactions between Jupiter, Saturn, and the outer planets often result in one large body being flung outward and lost entirely. In those simulations, Neptune itself is frequently ejected. Since Neptune is clearly still here, one way to resolve this is to assume there was another ice giant that absorbed the instability and was expelled instead. If that is correct, then even our own solar system may have ejected not just small rocks and comets, but entire planets. That idea leads to a striking conclusion. There may be rogue worlds drifting through interstellar space, some of them as large as planets, possibly carrying moons, and in extreme cases perhaps even subsurface oceans. These objects would wander the galaxy without a parent star, shaped entirely by their internal heat and whatever energy remains from their formation. The universe allows this kind of outcome naturally, without requiring anything unusual or artificial. There are also well-studied mechanisms that can eject smaller bodies. One example comes from Neptune's moon Triton. Triton orbits Neptune in the opposite direction from most moons, which is unusual. Moons that form around a planet typically orbit in the same direction as the planet's rotation. For many years, Triton's backward orbit was a puzzle. The most widely accepted explanation today involves a binary system. In this scenario, Triton was once part of a pair of objects orbiting each other. Binary systems like this are common among asteroids and small bodies. As this pair passed close to Neptune, the geometry of the encounter mattered. Triton happened to be on the side moving in nearly the same direction and speed as Neptune. That allowed Neptune's gravity to capture Triton, the companion object, moving in the opposite direction, was accelerated and flung away at high speed, escaping the solar system entirely. This kind of gravitational exchange is efficient and does not require fine-tuning. A similar process could explain how interstellar objects like 3I Atlas are created. It may once have been part of a pair or a larger system. A close encounter with a massive planet could have captured one object and expelled the other. Over millions of years, that expelled object would drift through the galaxy until it happened to pass through another star system, such as ours. These ejection processes are slow. When a planet or small body is expelled, it does not shoot out rapidly in human terms. Its speed is comparable to spacecraft like Voyager 1 or Voyager 2. At those speeds, reaching the nearest star would take tens of thousands of years, but the galaxy is billions of years old. There has been ample time for countless objects to travel vast distances between stars. This naturally leads to broader questions about life elsewhere in the solar system. When people ask whether there could be life on a planet like Jupiter, the first issue is definition. Jupiter does not have a solid surface. Any life there would have to exist in the atmosphere, suspended within the clouds. This idea has been explored seriously, including by scientists like Carl Sagan. Similar proposals have been made for Venus. Venus is a harsh world at the surface. Temperatures there reach hundreds of degrees Kelvin, far beyond what life as we know it could tolerate. But higher in the atmosphere, conditions change. There is a layer where temperature and pressure are surprisingly similar to those on Earth. A few years ago, scientists reported the detection of a molecule called phosphine in Venus's atmosphere. On Earth, phosphine is produced almost exclusively by biological processes. That discovery generated excitement and debate. The challenge is explaining how life could persist in such an environment. Any organisms would need a way to remain suspended in the atmosphere and survive acidic conditions. While speculative, the idea is not impossible. Scientists remain open to it, though it is not considered the most promising place to search. More attention is focused on icy moons such as Europa and Enceladus. These moons are believed to contain liquid water oceans beneath their surfaces, along with organic molecules and internal heat. On Earth, oceans are rich with life if similar environments exist elsewhere. They represent a more direct extension of conditions known to support biology. From a scientific standpoint, these are higher probability targets. This is why the search for life often prioritizes Earth-like planets and environments. It is not due to a lack of imagination. Scientists have proposed life on neutron stars, within stars, and even the idea that a galaxy itself could function as a living system. But when resources are limited, choices must be made. Missions are prioritized based on where life is most likely to be found, using what is already known to work. The same logic applies to human exploration. Discussions about settling Mars have been prominent for years. Technologically, reaching Mars is extremely challenging, even with powerful launch systems. Sending people there requires multiple steps, including refueling in orbit and sustaining life for long periods in deep space. Progress is being made, but many technical hurdles remain. Living on Mars would be far more difficult than many people realize. Mars has a very thin atmosphere, almost no oxygen, and limited accessible water. Taking off a helmet would result in suffocation within moments. In many ways, Antarctica is a far more hospitable environment. And even there, humans only stay temporarily. Mars would not be a place for casual settlement. It would require underground habitats, constant life support, and a willingness to live in extreme isolation. Still, exploring Mars has value beyond colonization. One compelling idea is to build structures beneath the surface of the Moon or Mars as long-term records of human existence. These would not be messages meant for immediate reply, but time capsules designed to last far beyond the lifespan of our civilization. Earth is a poor place for long-term preservation. Weather, erosion, plate tectonics, and biological activity erase structures over time. Cities would disappear within millions of years. The Moon, by contrast, has no atmosphere, no wind, no rain, and almost no geological activity. Footprints left there can last for millions of years. Objects placed on the Moon could plausibly remain until the Sun expands billions of years from now. Mars also offers advantages over Earth in this respect. It lacks active plate tectonics and has far less erosion. Structures placed underground could persist for extremely long periods. If another civilization were to explore the solar system in the distant future, these artifacts could be discovered and interpreted, much like archaeological sites on Earth. This approach accepts a limitation imposed by physics. Two-way communication with other civilizations requires both proximity and overlapping timelines. Signals travel at the speed of light. Civilizations must exist at the same time and close enough for messages to arrive within meaningful periods. Those conditions may be rare. One-way communication, preserved in physical form, avoids that constraint. It does not require the sender and receiver to coexist. It simply requires survival of the message. Earth itself is already visible as a remarkable planet. From far away, its atmosphere reveals oxygen, oceans, and signs of complex chemistry. These are strong indicators of life. Any advanced civilization observing the galaxy would likely identify Earth as unusual, even if they see it as it was tens of thousands of years ago. The biosphere alone would mark it as significant. For that reason, Earth stands out as a beacon. It is a planet where something complex is happening. Whether or not anyone ever comes to visit, the signal is already there, written into the light that leaves the planet and travels across the galaxy. Earth would stand out immediately to any distant observer searching for places of interest in the galaxy. One of the strongest signals that makes Earth unusual is oxygen in its atmosphere. Oxygen is not easy to produce in large amounts. On Earth, it is created almost entirely through photosynthesis. That process required a major biological innovation and did not appear until about 2.5 billion years ago. For the first 2 billion years of Earth's history, life existed only in simple microbial forms, relying on chemical energy rather than sunlight. Photosynthesis changed everything. Once oxygen began to accumulate in the atmosphere, it allowed for far more efficient ways for cells to generate energy. This made it possible for complex cells to evolve. These cells, known as eukaryotic cells, are the foundation of plants, animals, and humans. With more available energy, life could grow larger, more diverse, and more complex. Multicellular organisms appeared roughly 1 billion years ago. And from there, ecosystems expanded rapidly. Because of this sequence, An oxygen-rich atmosphere is widely seen as a strong indicator that complex life is present or has been present from far across the galaxy. An advanced civilization observing Earth would likely recognize this signal, even if they were 100,000 light-years away. They could detect oxygen and infer that something biologically interesting was happening here. What they would see, however, would be Earth as it was 100,000 years ago. Any attempt to travel here would take an enormous amount of time unless faster than light travel were possible. By the time a spacecraft arrived, the civilization that launched it might no longer exist. This raises an alternative possibility. Instead of traveling directly, a civilization could leave something behind. If observers detected early signs of life billions of years ago, they might predict that intelligence could eventually arise. They might choose to place a marker or a message, not for immediate contact, but for discovery far in the future. This idea appears in science fiction, but it also follows logically from the limits imposed by the speed of light. If such a time capsule were to be placed in our solar system, Earth would not be a good choice. Earth constantly erases its own history through weather, erosion, plate tectonics, and biological activity. Over tens of millions of years, even the largest structures disappear. The Moon, by contrast, is far more stable. It has no atmosphere, no wind, no rain, and almost no geological activity. Objects placed there can remain essentially unchanged for millions, or even billions, of years. The Moon also contains natural underground structures that make it especially interesting. Early in its history, the Moon experienced volcanic activity. Lava flowed beneath the surface, leaving behind large hollow tunnels known as lava tubes. These structures can be vast, some large enough to resemble underground cathedrals. They are naturally shielded from micrometeorites and radiation. If sealed, they could even hold an atmosphere. For humans, they would be ideal locations for future bases. For long-term preservation, they would be even better. Placing something inside a lunar lava tube would require very little excavation. The structure already exists. It would simply need to be accessed. These regions have not yet been explored directly, but orbital measurements strongly suggest they are present. From a long-term perspective, this makes the Moon one of the most durable archives available in the inner solar system. Active signaling methods, such as radio beacons, are far less reliable over deep time. They require continuous power and maintenance, even under ideal conditions. Such systems might last a few decades or centuries. Physical artifacts, by contrast, can survive without energy input. A carefully placed structure could remain intact long after its creators are gone. Discussions about returning to the Moon often raise a familiar question. Humans landed there in 1969, and several missions followed. Since then, no one has returned. This absence is sometimes misunderstood. Scientifically, the Moon has continued to be studied extensively through robotic missions, orbiters, and landers. What has been missing is a sustained human presence. The reason is largely political and economic rather than scientific. The original Moon landings were driven by geopolitical competition. They were a demonstration of technological capability and national prestige. Once that goal was achieved, the incentive disappeared. Sending humans to the Moon is extremely expensive, and there is little direct economic return. Moon rocks are scientifically valuable, but they do not justify the cost of repeated crewed missions. If the Moon were different, the story might have unfolded another way. If it were larger, with about 10% of Earth's mass instead of roughly 1%. It could hold an atmosphere. In that case, it might have been a habitable world. It sits at the right distance from the Sun, and it likely would have received water from comet impacts just as Earth did. In such a scenario, the Moon could have developed oceans, weather, and possibly life. Human history would have changed dramatically. A habitable Moon would have been settled early and continuously. Instead, the Moon is a dry, airless world. Mars, by comparison, offers more long-term potential. Even though it is still extremely hostile, it has a thin atmosphere, evidence of past water, and conditions that might be made marginally livable with advanced technology. This makes Mars a more compelling long-term target, despite being far more difficult to reach. Still, the Moon occupies a unique role. It is close enough to reach with relatively simple technology. It served as a stepping stone that allowed humanity to develop rocketry and spaceflight capabilities. Without it, progress in space exploration might have been much slower. Mars represents the next major step, more challenging but still achievable. Beyond that lies interstellar space, which remains far beyond current reach. The Moon itself is also unusual in another way. Relative to the size of its planet, it is the largest moon in the solar system. Its presence has influenced Earth's tides, climate stability, and even the development of life. Its role in human history and planetary evolution is outsized compared to its mass. Exploring the Moon's lava tubes is technically challenging but feasible. Traditional rovers cannot easily descend into steep openings. For that reason, engineers have proposed alternative designs, including tethered robots, rolling spheres, and snake-like machines capable of climbing and descending vertical shafts. Several space agencies have studied these ideas, and some have begun testing prototypes. International cooperation plays a major role in modern space exploration. Large projects often involve multiple countries contributing different components. Space telescopes, for example, are frequently built through joint efforts, with instruments developed in one region, launch vehicles provided by another, and operations shared across agencies. This collaboration has produced remarkable results. At the same time, cooperation is shaped by political realities. Some partnerships are strong, while others are limited by tension between governments. Even so, space has often served as a rare area of peaceful collaboration. On the International Space Station, astronauts and cosmonauts from different nations work together in close quarters. The selection and training process emphasizes cooperation and emotional stability, precisely because isolation and conflict would be dangerous in that environment. Space has no borders in the traditional sense. No nation owns the Moon. This creates both opportunity and uncertainty. Exploration proceeds through treaties and agreements rather than territorial claims. As activity increases, questions about governance, access, and responsibility will become more important. Throughout all of this, the underlying motivation remains consistent. Humans explore not only for resources or prestige, but to understand where we fit in the universe. Earth, with its oxygen-rich atmosphere and complex life, already sends a powerful signal into space, whether or not anyone is listening. That signal carries the story of a planet where chemistry turned into biology, and biology eventually began to look outward. Any long-duration space mission makes one thing very clear very quickly: you do not want someone difficult to live with, trapped in a confined environment for months or years. When everything depends on cooperation, temperament matters as much as technical skill. That reality has shaped how astronauts are selected and why missions are planned so cautiously. This concern connects naturally to another idea that often comes up when people talk about the moon, especially its far side. There has been persistent discussion about China showing particular interest in operating on the far side of the moon. That idea is not made up. China has indeed invested heavily in lunar exploration, and part of that interest is tied to radio astronomy. On Earth, radio telescopes face a growing problem. Our planet has become increasingly noisy in radio frequencies. Communication networks, satellites, radar systems, television broadcasts, and even everyday electronics flood the environment with signals. For astronomers trying to detect faint radio emissions from distant cosmic sources or potential signals from extraterrestrial civilizations, this noise is a serious obstacle. Radio telescopes themselves are relatively simple in concept, unlike optical telescopes, which require mirrors polished to extreme precision at the nanometer scale. Radio telescopes can be built from much rougher materials. Concrete, metal mesh, and naturally curved surfaces can be sufficient. This allows them to be enormous. The largest radio dishes on Earth stretch hundreds of meters across. For many years, the Arecibo Observatory in Puerto Rico was the largest and most famous radio telescope in the world. It made historic contributions to astronomy before being irreparably damaged and ultimately collapsing after severe storms. China has since built an even larger facility, known as FAST, the 500-meter aperture spherical telescope. It now holds the title as the largest single-dish radio telescope on Earth. The moon offers something Earth cannot radio silence. The far side of the moon is permanently shielded from Earth's radio emissions. It never faces our planet. As a result, it is one of the quietest radio environments anywhere nearby in the universe. From an astronomical perspective, it is an extraordinary location. A radio telescope placed there would be free from almost all human-made interference. There is another advantage as well. The moon's surface includes large craters that already have a dish-like shape. With relatively modest modification, some of these could potentially serve as natural foundations for radio telescopes far larger than anything feasible on Earth. For scientists interested in studying the early universe, faint cosmic signals, or even technosignatures from other civilizations, this is extremely appealing. China has already demonstrated its ability to reach the far side of the moon. In June of 2024, the Chang'e 6 mission successfully returned samples from the far side to Earth for the first time in history. The samples were collected from the South Pole Aitken Basin and delivered back to Earth for analysis. This achievement confirmed that far-side missions are no longer purely theoretical. During the Apollo era, astronauts never landed on the far side of the moon for a simple reason: communication. The far side blocks direct radio contact with Earth. Without relay satellites, astronauts would be completely isolated. If something went wrong, there would be no immediate way to help them. At the time, that risk was unacceptable. Robotic missions today can tolerate that isolation far more easily. The moon itself is surprisingly large. Although its mass is only about 1% of Earth's mass, its diameter is nearly 1/4 of Earth's. That translates into a land surface area roughly comparable to the continent of Africa. From a purely physical standpoint, there is a vast amount of terrain available for exploration, experimentation, and long-term projects. As conversations return to interstellar visitors and unusual objects like 3I Atlas, it becomes important to keep perspective. Not every anomaly implies artificial origin. When scientists examine lists of supposed anomalies, many turn out to be misunderstandings, statistical artifacts, or natural variations that only seem strange because they are unfamiliar. One of the claims made about 3I Atlas is that it contains less water than typical comets. Measurements suggest that water makes up only a few % of its gas plume by mass. While that may be somewhat lower than average, the key point remains that it is producing water at all. That behavior is fundamentally comet-like. Water outgassing is exactly what icy bodies do when warmed by a star. Some interpretations suggest a kind of Trojan horse scenario, where an artificial object disguises itself as a natural comet, but this idea quickly runs into problems. If an object were intentionally designed to appear natural, it would presumably do so convincingly. A disguise riddled with anomalies defeats its own purpose. The presence of oddities does not support the idea of deliberate camouflage. It undermines it. More broadly, invoking alien technology as an explanation requires extraordinary evidence. It is not enough for something to be unusual. It must violate well-established physical expectations in a way that cannot be explained by natural processes. Passing near planets, outgassing volatiles, and following gravitational trajectories are all behaviors we expect from comets and asteroids. That does not mean the search for extraterrestrial technology is misguided. On the contrary, it is reasonable and scientifically interesting. Dedicated searches for artificial objects, unusual emissions, or non-natural structures are worth pursuing. The issue arises when ordinary phenomena are prematurely labeled as alien without sufficient justification. There is also a broader risk. Overusing the alien explanation can actually harm serious inquiry. When every strange observation is framed as extraterrestrial, public trust in legitimate discoveries erodes. Scientific standards exist precisely to separate compelling evidence from speculation. As more interstellar objects are discovered, familiarity will grow. New observatories, such as the Vera Rubin Observatory, are expected to detect hundreds of interstellar visitors over the coming decades. What now feels rare and sensational will eventually become routine. With a larger sample size, patterns will emerge, and today's anomalies may look much less mysterious. Crucially, these objects matter regardless of whether they are artificial. Each one is a physical fragment from another star system. They are natural messengers, delivering information about environments we cannot yet reach. Studying them is equivalent to holding a rock from another solar system in a laboratory. If technology advances far enough, it may even be possible to intercept one of these objects. A spacecraft could rendezvous with it, land briefly, collect samples, and return them to Earth. In that sense, interstellar objects offer a shortcut around the enormous challenge of traveling between stars. There is nothing inherently unrealistic about such missions. With sufficient preparation, a spacecraft already positioned in the solar system could accelerate to meet an incoming object. Launching from Mars, with its lower gravity, would make this even easier. Future infrastructure could turn rare opportunities into routine missions. The scientific payoff would be extraordinary. These objects could preserve pristine material from their parent systems. Their chemistry might differ from anything found in our solar system. In the most exciting scenario, they could even contain traces of simple life, such as fossilized microbes or organic molecules shaped by biology. This is not speculation pulled from science fiction. We already study meteorites from Mars that have naturally traveled to Earth after impacts. Antarctica, with its ice fields, is one of the best places to find them. These rocks have taught us a great deal about Martian geology without ever drilling into the planet itself. Interstellar objects extend that principle to a galactic scale. They allow us to study distant systems without building starships capable of crossing light years. In a very real sense, The universe is bringing samples to us. For that reason alone, objects like 3I Atlas deserve attention and careful study. Whether or not they have anything to do with intelligent life, they are among the most valuable natural experiments available to astronomy. Reducing their importance to a binary question of alien or not alien misses the larger picture. They are records of other suns, other planetary systems, and other histories. They offer insight into how common planets are, how materials form, and how chemistry unfolds beyond our local neighborhood, even stripped of sensational claims. They remain profoundly significant. In that light, the real story is not disappointment if an object turns out to be natural. The real story is that nature itself is far richer and more interconnected than we once imagined. Interstellar visitors are reminders that our solar system is not isolated, but part of a constantly exchanging galaxy. Current tracking shows that the object's path is well understood. Right now, it is emerging from behind the sun from our point of view. Over the coming weeks, it will move back into clearer view and make its closest approach to Earth in mid-December. That closest approach is still very distant by astronomical standards. There is no scenario in which it comes anywhere near Earth itself. After that, it continues outward, passing near Jupiter sometime in the spring, and then steadily exits the solar system altogether, based on its trajectory. Astronomers expect to be able to observe it for roughly another year before it fades beyond useful detection. That predictable departure is important, as the object continues on a clean, gravity-driven path and leaves the solar system. It naturally undercuts more dramatic claims. If it simply passes through and never deviates, the idea of an intentional visit becomes much harder to sustain. Suggestions that it might suddenly release small probes during a close approach are technically possible in the most abstract sense. But there is no evidence pointing in that direction. One could imagine almost any extraordinary event without data to support it. Science depends on what is measurable, not on what is merely imaginable. There is also a more grounded concern that often comes up in these discussions. Humanity has a clear historical example of what happens when large objects strike Earth. The asteroid impact linked to the dinosaur extinction involved an object only a few kilometers across. Yet it altered the global climate and reshaped life on the planet. That raises a reasonable question. If an object like this, or another large comet or asteroid, were actually on a collision course today, could we stop it? In practical terms, nuclear devices remain the most effective last resort option. Contrary to popular depictions, the goal would not be to blow the object apart. Fragmentation would simply create multiple dangerous pieces following nearly the same trajectory. The preferred approach would be to detonate a nuclear device nearby, offset from the object, so the resulting energy gently but decisively nudges it onto a different path. The object stays largely intact but misses Earth. If more warning time were available, there would be gentler options. For known asteroids within our own solar system, whose orbits can be predicted decades in advance, even subtle forces can be enough, changing the surface reflectivity of an asteroid. For example, by coating one side with a lighter material, alters how sunlight pushes against it. Over years, that tiny pressure can shift the orbit enough to avoid an impact. That technique relies on time, not force. Interstellar objects pose a greater challenge because they move much faster. Their high velocities mean detection often comes late. A body only 100 meters across could still devastate a major city, yet might be spotted only weeks before arrival. In that scenario, response time becomes the limiting factor. Coordination, resources, and preparedness would matter far more than theoretical capability. That context leads back to the ongoing analysis of 3I Atlas itself. As the discussion turns to the remaining anomalies on the list, it becomes clear that many of them hinge on limited statistics. Claims of unusual polarization, for example, sound dramatic in isolation, but when comparisons are drawn against only two other interstellar objects, conclusions remain fragile. With a larger sample, what seems extreme today may look ordinary tomorrow. Patience matters. Another claim links the object's incoming direction to the so-called wow signal, a strong radio burst detected in the 1970s that has never been repeated, while the wow signal remains unexplained. The angular separation involved here is large. In cosmic terms, a difference of several degrees corresponds to vast distances, often tens of thousands of light years. That is not spatial coincidence in any meaningful physical sense. Without far tighter alignment, the connection does not carry weight. Brightness behavior near perihelion has also been highlighted. The object did brighten rapidly and showed a bluish color relative to the Sun. That observation is accurate. But speed matters. This object is moving faster than any comet previously observed. A rapid brightening under intense solar heating is not surprising under those conditions. When behavior scales with velocity, apparent extremes often resolve into expected outcomes. The final anomaly on the list concerns non-gravitational acceleration and mass loss. Yet mass loss driven by evaporation is precisely what defines comets. As ice and volatile materials heat up, gas escapes, producing small thrusts that alter motion slightly. Losing a significant fraction of mass near the Sun is normal for icy bodies. In this respect, the object behaves exactly as cometary physics predicts. There is a broader pattern worth noticing. Over time, the list of anomalies has grown, while ordinary behaviors receive less attention. Features that initially seemed inconsistent, such as the absence of a visible coma at great distance, later resolved naturally as the object moved closer to the Sun. When new data contradicted earlier interpretations, the hypothesis shifted rather than being discarded. That flexibility may sound appealing, but it weakens scientific rigor. A hypothesis that can adapt to any outcome explains everything and therefore explains nothing. This highlights a fundamental issue with invoking extraterrestrial intelligence as a default explanation. It is too flexible. It can be used to account for any observation without ever being testable. Science requires hypotheses that risk being wrong. When evidence contradicts them, they must be revised or abandoned, not endlessly reshaped. None of this dismisses the search for extraterrestrial intelligence itself. The search is valid, important, and worth sustained effort. But extraordinary claims demand extraordinary evidence. Clear signs would include deliberate maneuvers, artificial signals, or behaviors that violate known physical laws. Without such evidence, restraint is not skepticism for its own sake. It is discipline. Importantly, disagreement does not imply disrespect. Proposing bold ideas invites scrutiny. And scrutiny is the mechanism by which science advances. Challenging a hypothesis is not an attack on the person who proposed it. The healthiest scientific culture allows strong disagreement without personal hostility. In this case, most evidence points toward a natural explanation. The object's motion, composition, and evolution fit within the range of cometary behavior. Even if some aspects sit near the extremes of that range, that makes it interesting, but not artificial. What truly matters is what these objects represent. Each interstellar visitor is a fragment of another planetary system. They carry physical records of environments shaped by different stars. Studying them deepens understanding of how common planets are, how materials form, and how chemistry varies across the galaxy. With future surveys, interstellar objects will become more common discoveries. As familiarity grows, the temptation to sensationalize each one will fade. The scientific value, however, will only increase. These bodies offer a practical way to study other star systems without traveling light years. The goal is not to believe or disbelieve for emotional reasons. The goal is to reach conclusions so robust that even skeptics accept them. That standard applies to every scientific claim, from new particles to new planets to potential signs of life. When evidence eventually reaches that level, debate will end naturally. Until then, caution is not a failure of imagination. It is a commitment to truth. That attitude carries over naturally from entrepreneurship into science. Progress almost never comes from getting everything right the first time. It comes from repeated attempts, careful failures, and learning where the edges really are. In business, a failed startup is often treated as experience rather than disgrace, especially in places that value risk-taking. Science works the same way at its best. A bold idea that turns out to be wrong is not wasted effort if it sharpens methods, clarifies assumptions, and forces better data to be collected. That is why it would be a mistake to permanently dismiss someone simply because one high-profile hypothesis does not hold up, even if this particular case turns out to be wrong. That does not mean future ideas from the same person should be ignored. Evidence should always be judged on its own merits. If good data appears, it deserves attention, regardless of who presents it. Scientific progress depends on that openness. Flying too close to the sun sometimes melts the wings, but refusing to fly at all guarantees stagnation. Curiosity usually starts early. For many scientists, fascination with space begins long before formal training. Science fiction, astronomy books, and the sheer strangeness of the night sky leave a lasting impression. The realization that invisible particles are passing through your body every second, that stars are unimaginably distant yet governed by understandable laws, can be genuinely transformative. That sense of wonder often becomes the fuel for years of study. Choosing astronomy over other branches of physics can also be a practical decision. Modern fundamental physics often requires enormous collaborations and massive financial investment. Individual contributions matter, but they can feel diluted within projects involving thousands of researchers. Astronomy, by contrast, offers a vast observational playground. There are hundreds of billions of stars in the Milky Way alone. Far more targets than any single lifetime could exhaust, even with billions of people on Earth. There is no shortage of unexplored systems. Discovery feels accessible in a very direct way. That sense of abundance is especially clear in the study of exoplanets. An exoplanet is simply a planet that orbits a star other than the Sun. The term comes from extrasolar, meaning outside our solar system. For most of human history, planets were known only around our own star. Today, thousands are known around other stars, and that number has grown rapidly in just a few decades. The explosion of discoveries began roughly 20 to 25 years ago. Since then, astronomers have confirmed on the order of 5,000 to 6,000 exoplanets, with new ones added every year. For a young researcher entering the field during that period, it felt like arriving at the start of a gold rush. Entire classes of worlds were being discovered for the first time, and even individual scientists could realistically expect to find planets themselves. There are several methods used to detect exoplanets. But one of the most productive is the transit method. Directly imaging most planets is impossible because they are too faint and too close to their much brighter stars. From vast distances, the star and planet blur into a single point of light, but if the geometry is favorable, a planet will periodically pass in front of its star from our point of view. When that happens, the star's brightness dips slightly. These tiny dips are what astronomers look for. A star that dims regularly, say every 10 days, suggests a planet with a 10-day orbital period. That period defines the length of its year. Repetition is crucial. A one-time dip could be noise or some unrelated event, but a consistent pattern signals an orbiting body. The depth of the dip reveals the planet's size. If the planet's radius doubles, it blocks 4 times as much light. That means large planets are much easier to detect than small ones. Early discoveries were dominated by Jupiter-sized worlds and Neptune-sized worlds. Over time, as instruments improved, Earth-sized planets became detectable as well. At the current limits, detecting objects smaller than Earth is extremely challenging. Though in rare cases, bodies approaching the size of the Moon can be inferred. One of the most famous exoplanet systems discovered so far is known as TRAPPIST-1. It consists of a small, cool, red star orbited by 7 planets that are all roughly Earth-sized. 3 of those planets lie within what astronomers call the habitable zone, meaning the distance from the star where temperatures could allow liquid water to exist on the surface, assuming suitable atmospheric conditions. The star itself is much smaller and cooler than the Sun, with a mass roughly 1/8 that of our star. Because it is so dim, its habitable zone lies very close in. All 7 planets orbit closer to their star than Mercury does to the Sun. In cosmic terms, the system is compact. If an advanced civilization existed there, interplanetary travel within the system would be relatively easy. Material exchange between planets could even happen naturally through impacts ejecting rocks from one world to another. Despite its exotic configuration, TRAPPIST-1 is close by astronomical standards, at a distance of roughly 30 light-years. That proximity makes it an ideal target for detailed study. The James Webb Space Telescope has devoted significant observing time to this system, analyzing how starlight filters through the planet's atmospheres during transits. So far, observations have shown that the 2 innermost planets lack substantial atmospheres, likely stripped away by stellar activity. That result already demonstrates the power of modern instruments. For the remaining planets, especially the one designated TRAPPIST-1e, data collection is ongoing. Scientists are trying to determine whether an atmosphere exists at all, and if so, what gases it contains. Atmospheric characterization relies on the same transit technique used to find the planet in the first place. When a planet passes in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. Different molecules absorb light at specific wavelengths. By measuring these subtle spectral fingerprints, astronomers can infer the presence of gases such as water vapor, carbon dioxide, methane, or potentially oxygen. This process is extraordinarily difficult. The signals are faint, and multiple transits must be combined to build up enough data. Even with the most advanced telescopes available, there are limits to what can be detected. For now, the question of whether any TRAPPIST-1 planet has an Earth-like atmosphere remains open. Still, the broader implication is already clear. Planets are common. Earth-sized planets are common. Multi-planet systems are common. The universe is not short on places where life could potentially arise. Each new detection adds context, reduces uncertainty, and sharpens the questions scientists know how to ask. That perspective loops back to the earlier discussion about caution and openness. Discovery rarely arrives fully formed. It emerges gradually, through partial answers and refined methods. Being wrong along the way is not a flaw. It is a necessary step. What matters is the willingness to adjust beliefs when evidence demands it, and the discipline to separate what is fascinating from what is demonstrated. In that sense, the search for planets, for life, and even for intelligence elsewhere in the universe is not about dramatic conclusions. It is about building a framework sturdy enough that, when something truly extraordinary appears, it will be recognized for what it is. Imagine observing the same planet transit its star, but doing so at different colors of light. You watch the starlight dim as the planet passes in front, just as before. Now you repeat the measurement in blue light, and then again in red light. On Earth, the sky appears blue because the molecules in our atmosphere scatter blue wavelengths very efficiently. If Earth had no atmosphere, the sky would look black, even during the day. That same principle applies when observing a distant planet. In blue light, Earth's atmosphere blocks and scatters much of the incoming starlight from far away. The planet appears slightly larger, because you are seeing not just the solid surface, but the extended envelope of the atmosphere as well. In red light, the situation is different. Red wavelengths pass through the atmosphere with far less interference. In that case, the planet appears smaller, closer to the size of the rocky body alone. By comparing how large a planet appears at different wavelengths, astronomers can infer what gases are present in its atmosphere. This technique can be pushed further by examining very narrow slices of the spectrum. Specific molecules absorb light at precise wavelengths. Carbon dioxide, for example, absorbs strongly at a wavelength of 4.6 microns. At that exact wavelength, the planet suddenly appears larger, because the atmosphere is opaque there. At nearby wavelengths, the size returns to normal. That jump is a clear signature of carbon dioxide. In this way, astronomers are effectively reading the chemical composition of an atmosphere from light alone. It is not a literal sense of smell, but the analogy is useful. The spectrum carries information about what the atmosphere is made of, much like scent carries information about chemicals in the air. By breaking the light apart and measuring where it is absorbed, the composition becomes visible. Different research teams approach this work with different goals. Some focus on discovering as many new planets as possible. Others concentrate on understanding a smaller number of systems in great detail, after thousands of planets have already been cataloged. Simply adding more to the list is not always the most compelling objective. The frontier shifts toward questions that have never been answered before. One such frontier is the search for exomoons, moons that orbit planets around other stars. At present, there are no confirmed exomoons. None. Despite decades of observation, not a single one has been conclusively detected. There are a few promising candidates, identified using data from space telescopes such as Hubble, Kepler, and the James Webb Space Telescope. But confirmation requires repeated observations. The challenge is subtlety. A planet produces a clear, repeatable dip in starlight. A moon produces a much smaller signal, often only visible once or twice. A single dip could be caused by noise, an instrumental effect, or a transient event. To claim a discovery, astronomers need consistency. That means seeing the same pattern again and again, under different conditions, with different instruments. Finding exomoons would matter for several reasons. First, moons themselves could be habitable. In some systems, a large moon orbiting a gas giant might have liquid water, an atmosphere, and stable conditions suitable for life. Second, moons can strongly influence the habitability of their host planets. Earth's own moon plays an important role in stabilizing the planet's axial tilt. Earth's axis is tilted by about 23 degrees, and that tilt remains relatively stable over long periods of time. Without the moon, the tilt would wander over millions of years. The poles could point closer to the sun, then farther away. Such variations would produce extreme climate swings, with severe consequences for long-term habitability. Tides are another factor. While tides would still exist without the moon, they would be much weaker. Early in Earth's history, when the moon was far closer than it is today, tides were enormous. Large portions of continents were regularly flooded. While that would be disastrous for modern cities, it may have been helpful for the origin of life. Repeated flooding and drying creates natural chemical concentration zones, such as tidal pools, where complex chemistry can occur. Beyond moons themselves, understanding moon systems is critical for interpreting future images of Earth-like exoplanets. One of the long-term goals of astronomy is to directly image a pale blue dot around another star, a distant planet seen as a tiny point of light. Similar to the famous image of Earth taken by a Voyager spacecraft from the outer solar system, that photograph shows Earth as a faint blue speck, barely distinguishable from the background. One day, future telescopes may capture similar images of exoplanets. When that happens, scientists will analyze the light from those dots to search for signs of life. Oxygen is one such sign, but it is not definitive on its own. Oxygen can be produced without life through the splitting of water molecules by stellar radiation, a process known as photolysis. Methane is often proposed as a companion indicator. On Earth, methane is strongly associated with biological activity. However, methane can also exist naturally. Saturn's moon Titan, for example, has vast amounts of methane with no known life. If a lifeless planet had a small amount of oxygen and a methane-rich moon, the combined light from the system could mimic the chemical signature of life. Without knowing whether a moon is present, astronomers could be misled. A planet-moon system might look alive when it is not. That is why identifying moons is not just an added detail. It is essential for correctly interpreting atmospheric signals and avoiding false positives. The effects of multiple moons depend on their masses and orbits. In our own solar system, Jupiter's 4 largest moons provide an example. Their gravitational interactions create tidal heating, orbital resonances, and internal energy sources. Europa, one of those moons, likely has a subsurface ocean kept warm by tidal forces alone. In other systems, multiple moons could stabilize or destabilize climates, alter rotation rates, or drive geological activity. All of this highlights a broader point. Habitability is not determined by a single factor. It is the outcome of many interacting elements: stellar type, orbital distance, atmospheric composition, planetary rotation, magnetic fields, and the presence or absence of moons. Understanding those interactions requires patience, careful measurement, and a willingness to revise assumptions as new data arrives. As observational tools improve, these questions move from speculation toward testable science. Each new technique adds another layer of information, Each confirmed detection sharpens the picture. The goal is not simply to find something extraordinary, but to understand it well enough that its significance is unmistakable when it finally appears. Io is one of the most extreme examples of how moons can be shaped by gravity. It is intensely volcanic because it is caught between competing forces. Jupiter's gravity pulls strongly inward, while neighboring moons tug outward as their orbits shift. The result is constant stretching and squeezing of Io's interior. Rock is flexed again and again. Heat builds up, and volcanoes erupt across the surface. It is not driven by internal radioactivity alone, but by gravity itself. Working like a slow mechanical pump, moons do not stay fixed forever. Orbits evolve. Our own moon is drifting away from Earth by about an inch each year. Over billions of years. That separation adds up. In principle, planets can lose moons, or moons can migrate into new configurations. The moon was once much closer, appearing far larger in the sky. As it continues to recede, its apparent size slowly shrinks. One consequence is subtle but striking. Total solar eclipses will not last forever. The moon currently appears almost exactly the same size as the sun in the sky, allowing it to block the solar disk perfectly. In the distant future, that alignment will be gone. Eclipses will become partial and then disappear entirely. That coincidence alone is unusual. A moon with just the right size, at just the right distance, orbiting in nearly the same plane as its star, is rare. From a distance, a system like Earth's would stand out. It would not look ordinary. Even our broader solar system appears uncommon. Only about 10% of stars host a Jupiter-sized planet. Our system has two gas giants of that scale, and despite thousands of known exoplanets, no true Earth analog has yet been found. That does not mean they do not exist. Only that the universe is vast and our sample is still small. Speculation about advanced civilizations quickly runs into limits. If a civilization is far beyond us technologically, its actions may be indistinguishable from natural processes. What looks like nature to us could, in principle, be engineered on scales we cannot imagine. Stars, galaxies, even large-scale cosmic structure might be artificial, and we would have no way to tell. Science, however, is built on a practical assumption that the universe behaves according to natural laws. That assumption has worked. It allows prediction, testing, and progress. Without it, there is no clear way to proceed. Questions about fine-tuning push science toward its edges. Certain physical constants appear delicately balanced. The masses of fundamental particles differ by small margins that allow atoms to exist. Change those values slightly, and stable matter disappears. There are two common responses. One is that the universe was designed this way. Another is that many universes exist, each with different values, and we naturally find ourselves in one that permits life. This is the multiverse idea. Modern cosmology gives some support to this second view through the theory of inflation. Inflation explains why the universe looks the same in all directions and why distant regions share similar properties despite having no time to communicate under ordinary expansion. The theory predicted features in the cosmic microwave background that were later observed. In most versions of inflation, a multiverse follows naturally. Regions of space inflate into separate bubbles, each potentially with different physical laws. This raises a difficult question. If other universes can never be observed or tested, does talking about them still count as science? Inflation itself makes testable predictions and has passed several by the multiverse. However, may remain beyond direct evidence. It sits at the boundary between physics and philosophy. It is not invoked lightly, but it is also not easily dismissed. Time travel often enters these discussions, but physics places strong limits there as well. Traveling forward in time is straightforward through relativity. Traveling backward introduces deep contradictions. Even hypothetical mechanisms like wormholes run into instabilities. Small quantum effects would amplify, creating runaway energy that destroys the structure. The universe appears to protect its own consistency. Backward time travel likely breaks too many rules to be allowed. These boundaries matter because science depends on restraint as much as imagination. Ideas must be bold, but they must also face evidence. Hypotheses that explain everything explain nothing. Progress comes from narrowing possibilities, not expanding them without limit. That balance also matters when thinking about the future of space science. Government agencies like NASA have always relied on private industry to build hardware. That is not new. What is new is the scale of private involvement. Lower launch costs and reusable rockets have changed what is possible. Collaboration can be powerful, but fundamental science is different from engineering. It rarely produces immediate returns. Discoveries that shape civilization often take decades to show their value. Private funding tends to focus on near-term outcomes. Basic research does not fit that model well. Studying distant galaxies, exoplanets, or the origin of the universe enriches knowledge rather than profit. Yet those pursuits are part of what defines a civilization. They are closer to art than to industry. They satisfy curiosity, expand perspective, and inspire future generations. Astronomy, in particular, has always served as a gateway. It draws people into science through wonder rather than utility. Many who start by looking at stars go on to become engineers, doctors, and innovators. The initial spark comes from something that does not obviously pay off. That spark still matters. Maintaining that sense of wonder requires investment, communication, and patience. Public engagement plays a role. When complex ideas are shared clearly and honestly, they reach people who may never have encountered them otherwise. Somewhere, a young listener hears about moons, planets, or distant stars and begins asking questions. That process cannot be measured in quarterly returns, but it shapes the future all the same. Work continues along those lines. New telescopes, new missions, and new theories are steadily refining our understanding. At the same time, broader reflections continue about where humanity fits in the larger picture. Those reflections are not separate from science. They are part of why the questions are asked in the first place. That perspective also feeds into longer projects, including efforts to write and synthesize these ideas more fully, exploring what we know, what we think we know, and where uncertainty remains is an ongoing process. Some of that work is already written. More remains to be done.